How's it going, everyone? My name is Salman, and I wanted to make a series of videos for everyone covering the basics of organic chemistry as well as some other topics, maybe in biology. In this video, I wanted to go over the relative stability of alkenes, and I've drawn here for you 4 different alkenes, and I've written their specific heats of combustion below. As you can see, the alkene that has the lowest heat of combustion is this alkene right here. It's the 2-methylpropene, and there's a specific reason for it that I'll go over in a little bit. One thing to take note of is that all 4 of these alkenes, the cis-2-butene, 1-butene, trans-2-butene, 2-methylpropene, all of these alkenes have 4 carbons in them. As you can see, there's 1 carbon here, 1 carbon here, 1 here, and 1 here. So all 4 of these have 4 carbons, but as you can see, their relative heats of combustion vary. So one thing that I wanted to mention is that as the heat of combustion goes down from left to right, there is increasing stability in these molecules. And that makes sense because a less stable molecule will have a higher heat of combustion because it's unstable. But there are 3 real reasons for why this occurs. And the very first reason for why there's increasing stability as we move down in the heat of combustion chain has to do with the degree of substitution. So I'm going to write that down first. The degree of substitution. Now, what the degree of substitution is talking about has to do primarily with the double bond. So as you can see, the double bond in the 1-butene is all the way at the beginning of the molecule. And when we talk about degree of substitution, we're talking about what branches or what carbons are coming off of that double bond. If you look to the left of this double bond, right here, there's no carbons coming out of it. There are 2 hydrogens coming out of here, 1 and 2, but we're going to disregard those for now. Over here on this side of the double bond, there is a connection to another carbon down here. So this connection, I would say, is a 1 degree of substitution. So I'm just going to write 1 degree. If we move on to the cis-2-butene, if we look at the end of the double bond over here and over here, there's 2 carbons coming out of it. 1 carbon on the left side, 1 carbon on the right side. So this one has 2 degrees of substitution. If we move on to the trans-2-butene, let's look at the double bond. The double bond on the right side has an extension out towards the carbon, and on the left side 1 extension as well. So this is again 2 degrees of substitution. If we look at the last molecule, on this side of the double bond, there's 2 carbons coming out, okay, and on this side of the double bond there's nothing going on. So this has 2 degrees of substitution. So these are what I mean by degrees of substitution, and they're really important for determining how stable the alkene will be. And basically the general rule is that the greater the degree of substitution, okay, the more stable the molecule is. And this is the general rule that you should remember for alkenes with multiple double bonds, or a molecule which is, if your professor tells you to compare 2 different molecules, you really want to first look at the degree of substitutions that molecule has on the double bonds. Okay, the second factor in alkene stability has to do with what we call van der Waals strain. And you may have heard of this in your general chemistry course. So I'll just write van der Waals strain here. And this typically deals with strain in cis compounds. So van der Waals strains, they can also be simply called steric effect. And this is when we're dealing with a molecule that has competing atoms or competing elements fighting for space. You can think about it that way. So I'm going to draw real quickly a two molecules. Let's choose the 1-butene and the cis-2-butene, and let's take a look at them. Okay, so let's look at the two molecules. We had 1-butene and we had cis-2-butene. Okay, so when we're looking for van der Waals strain, what you want to look for are the competing molecules. So if we look at this 1-butene here, there are two hydrogens coming off of it. Okay, there's two hydrogens here, and there's three hydrogens on this carbon right here. There's also one hydrogen over here. Okay, so that's this molecule. If we look at this molecule, got a hydrogen here, here, and there's three hydrogens over here, three hydrogens up here. Okay, now comparing these two molecules, let's look at what where the bulky groups are. This is a bulky group. Okay, there's three hydrogens there. Over here, we've got one bulky group here and one bulky group here. Okay, so if you look at it, this molecule has two bulky groups competing for space. So that would lead you to think this molecule is unstable compared to the one on the left. But as we know, the first rule is the degree of substitution. Okay, and the degree of substitution rule tells us that 1-butene, given that it has one substitution on the double bond versus the cis-2-butene, which has two substitutions on the double bond, tells us that the 1-butene is actually less stable. Okay, so you can't, what I'm trying to explain is that you can't simply look at the second rule, which is the steric effect, unless you consider the first rule. You have to go step by step. Now let's compare these two molecules. We have cis-2-butene on the left and trans-2-butene on the right. When we're considering the second rule, which is the steric effect, let's compare what's going on between these two molecules. So we have a methyl group over here on the trans-2-butene and another methyl group right here. On the cis-2-butene, we have a methyl group here and here. It's quite obvious if you look at it that the two methyl groups are competing for space in the cis-2-butene, whereas the two methyl groups are not really competing for space in the trans-2-butene. In fact, they're far away from each other. They're trans. Okay. However, it's important to note that we don't start looking at van der Waals strain first. We begin with the degree of substitution, which is why, as I mentioned earlier, when we're looking at the molecule 1-butene, you may immediately see this methyl group and it's not really competing for space. And you look at the 2-butene and you see that the cis-2-butene, and you see that these two methyl groups are competing for space, which may lead you to think that this is more stable than the cis-2-butene, but it's not. And the reason for that is, again, the degree of substitution. There's 1 degree of substitution on the double bond versus the cis-2-butene, which has 2 degrees of substitution. So that favors out the cis-2-butene automatically being more stable than the 1-butene because it has greater degrees of substitution. Only if we were dealing with the compounds such as the cis-2-butene and the trans-2-butene, you can see they both have the same degrees of substitution. They have 2 degrees of substitution right here and right here. So in that case, you need a tiebreaker, and the tiebreaker comes in with the steric effect or the van der Waals strain. Okay, and if we consider the steric effect, we see that the cis-2-butene has this competing effect versus the trans-2-butene, which does not compete. So in this case, the trans-2-butene would be more stable than the cis-2-butene. So the final rule in determining the stability of alkenes is chain branching. And let's compare these two molecules. We have trans-2-butene and 2-methylpropene. Fine. Now, can you tell just by looking which one has a chain and which doesn't? It may not be easy to tell, so I recommend looking at the name. If you don't have the name, then you can simply look at the parent chain. If you see here, this is a 1, 2, 3, 4 carbon molecule. The same here, 1, 2, 3, 4. It's a 4 carbon molecule. However, this 4th carbon is coming off of a main chain which looks like this. Whereas if I look at this 4th carbon, it's actually part of the main chain, which looks like this. So that's where the difference comes, and that's where this branching rule comes into effect. There's another way to do it. You can look at the name. So if I see butene, I'm going to start by drawing out a butane. I see the number 2, so I'm going to put the double bond on the 2nd carbon. And I see that it's trans, so these two methyl groups should be opposing each other, which they are. If it were cis, it would look like this. But it's not cis, it's trans. For the 2-methylpropene, how would I draw it? I'll start by drawing out a propane. Since I'm not shown a number, it's assumed that the 1st carbon has a double bond. And there's a methyl coming out of the 2nd carbon. So I'll draw it like this. So just by how you draw it, or your approach to drawing it, you can see that there is a substituent when I drew the 2-methylpropene. When I drew the trans-2-butene, I simply went ahead and drew a 4-carbon chain. However, with the propene, I started with the 3-carbon chain, and then ended up putting a double bond and the methyl group at the end. So that shows that there's a branch on the 2-methylpropene. This is just a long drawn-out way of determining if you have a branch on your molecule if you can't easily see it in the molecule above. But going on to the rule, the more branched molecule tends to have greater stability, which is why in this example, the trans-2-butene actually has a higher heat of combustion. The heat of combustion for trans-2-butene is 2,707 kilojoules a mole, whereas the heat of combustion for 2-methylpropene is 2,700 kilojoules a mole. So the 2-methylpropene is more stable than the trans-2-butene. So just to recap the rules, the very first rule you want to look for is the degree of substitution on the molecule. So the example given up here, the 1-butene has 1 degree of substitution, which I've circled here in red. The cis-2-butene has 2 degrees of substitution. The second rule you want to look at is the van der Waals strain, the steric effect. In the trans-2-butene, the 2 methyl groups are opposing each other, thus there's not great steric strain, versus the cis-2-butene where they're right next to each other, thus causing steric strain. So the trans-2-butene would be more stable. Finally, looking at chain branching, this rule tells us that a molecule with a branch coming off of its parent chain will tend to be more stable than a molecule without. So in this example, the 2-methylpropene is more stable than the trans-2-butene on the left. Thank you for watching this video. Please like, comment, and subscribe. If you have any further questions, feel free to leave me a comment. Thanks.